Hi, and welcome to Presidio.codes. In this video, we're going to look at deploying an MPLS network on Cisco VIRL using nothing but Ansible. So as you can see here, the topology for this video is 8 routers in the middle here acting as provider edge routers in an MPLS network. And then there are 4 customer edge routers at the 4 corners of this topology, which would simulate a customer that has a layer 3 VPN over the MPLS. Let's take a look at the code first, and then let's go ahead and start the simulation. So while we're going through the code, this will be starting up. All right, so this is a standard Ansible playbook. We have our deploy.yaml file, which is going to kick everything off. And then we have our Ansible configuration file for this playbook. And then we have our roles directory, group vars, and host vars. As well as an inventory file specifically for this project. So let's look at the inventory file first, and we're going to see there's some variables that I've set for all of the routers, and it's the username, password, the network operating system, and then we have a special command here for SSH. And what this allows us to do is tunnel all of our Ansible connections through the VIRL LXC container, because we don't have direct access to the management network that these routers are on. So this is just using it as a jump host. All right, so we have our customer edge routers and some variables to go along with those. And then we have 4 locations set up, and each of those has 2 PE routers and a CE router contained. And then we have some further subgroupings. We have a group of route reflectors. So in a IBGP, we'll have 2 route reflectors in this topology, and then all of the rest of the MPLS routers will be route reflector clients. And then we have the 4 CE routers at the corners. So that's our inventory file. And now let's look at further in the directory structure here. We have group vars. So we have all.yaml, which are variables that apply to the entire environment, so to every single host in the inventory. A few things. This is where do we store the output configurations that this playbook will generate. Some global MTU settings that we want to have. We want our MTU to be consistent across this entire environment, so we're going to set it globally. Same with OSPF. We would like, for instance, auto cost reference bandwidth. We want that to be the same across every OSPF speaker, so we're going to put it in all.yaml. And then we have a manual cost variable, because on certain ones of these links I'm doing manual OSPF costing to deprefer paths. And then we have global BGP settings for MPLS. We have the ASN. And then we have some other variables for test loopback interfaces when we deploy. So that's all.yaml. It applies to everything. There is a route reflectors clients and a route reflectors YAML file that I had put here in the beginning. I ended up not using them, but you can see that any variables declared there would only take effect on these 2 groups. All right, so let's look in our host vars. So host vars are different. If you think about a network device, there's certain settings and certain things like MTU and OSPF auto cost reference bandwidth that are for everyone, but there are certain things like IP addresses, VLANs perhaps, that are device specific. So for each one of these, we have declared all of our device specific variables for each of our routers. So we can see the host name, that's obviously device specific, a router ID as well, and then some circuit specific information that varies depending on what device you're on, etc. So that kind of takes care of all of our variables in this structure. Now, let's look at our deploy.yaml file. This is what's going to kick everything off. So when we're at the command line and we want to run this, you're going to call the deploy.yaml. What it's going to do is first it's going to connect to the route reflector devices and install the PERR router role, which stands for the Provider Edge Route Reflector Router role. And as you see in the directory structure, there's a folder called roles, and each of these subdirectories contains a bunch of tasks that are responsible for deploying that role to a router. Excuse me. So the next one is going to connect to Route Reflector clients and do the same thing, except this time it's going to install the role PERRC for Route Reflector client. And then third, the CE routers group of hosts in the inventory. We're going to install the CE router role on those. All right, so if we look at the first one, let me open that back up. The first one's going to be PERR router, so let's take a look at this one. Inside, it's got some folders. We're not using them all, but they're there if we need them. The main thing that we're doing here is tasks. When you make a role, it's going to be under tasks and then main.yaml. So these are the main tasks that are required in order to push a configuration out to the router to configure the route reflector role. So the first play in this, or the first task in this role, is to create the configuration output directory. So our base output directory, if you recall, was set in our group vars. So we're setting it to the local, whatever the current directory is, /output. So once we run this, you'll see an additional directory appear that has all our configurations in it. And then the second task is to create a route reflector configuration. So we're actually going to be referencing a Jinja template file and generating a configuration, and then we're storing it in that output directory with the file name of this router.conf. And then lastly, we're going to push the configuration. So we're actually connecting using the IOSXR config module. It's one of the Ansible network modules that they have available. So it's going to take that source configuration that we just wrote to disk. It's going to read it in, and it's going to connect to the device and deploy that configuration. All right, so let's look at task number 2, our Jinja templating. So we need to generate a template file. So let's there's a subdirectory here called templates, and our route reflector.j2 file is in here. Now this should look pretty familiar. It's a Cisco configuration, but instead of a real configuration, we've templatized it and put in variable placeholders. So, you know, the whole templating process is nothing more than a glorified find replace with a little bit more advanced features, but basically that's what it is. So you can see that on line 1 here, host name is host name, and the Jinja 2 syntax is double curly brace space and then the variable name and then closing it out. So that's how you do the substitution. Now, there are some advanced things in Jinja templating which makes it even more powerful, and that's loops, if statements and loops, you know, like a typical programming language. So you can see here, this is a for loop. We'll say for VRF in VRFs. So let's look back and you'll say, well, what is VRFs? If you look in all.yaml, we've defined here a VRF. And in the context of MPLS, a VRF is a layer 3 VPN. So if you were to buy a layer 3 VPN service from a provider, they're going to provide you a VRF on their network. It gives you transport between your sites that are a member of this VRF, and it crosses over their network, and it's using MPLS under the covers. So in this case, there's actually 2 separate VRFs, customer A and customer B. So as you can see, if we go back to the template for VRF and VRFs, we'll say VRF and then the name of the VRF, and we'll give it our MPLS ASN colon the route target. And then again, we're going to do the import export on that. And then we have down here end for, which ends the for loop. So in our case, we have two VRFs. We have two customer layer 3 VPNs we want to configure. So when you look at the output file that this will generate, there's going to be two stanzas that's created. One stanza for each VRF. So that's nice. Same goes for interfaces and other things. You can use for loops to generate all the lines, or for an unknown number of objects that you need to create, you can just run a for loop over it. So, you know, I don't have to change the template at all. If I want to add additional VRFs, I just add them to the variables file. Okay, so again, if you're looking in the BGP configuration, similar thing here. We've got for loop, and this is for route reflector and MPLS route reflector loopback addresses. If, so here's an if statement, which is nice. So we say if the route reflector is not equal to the current loopback address, then we go ahead and configure a neighbor statement. So basically what I'm doing here is we have two BGP peer groups. We have a peer group for route reflectors, and then we have a peer group for route reflector clients, and the configuration is slightly different. So depending on whether that neighbor is going to be a route reflector or a route reflector client is going to depend, you know, which set of settings that we assign to it. All right, so that's Jinja templating in a nutshell. There's a lot more to it, but there's plenty of documentation online. It's not just specific to network programmability. Jinja 2 is a general Python templating language that is used in lots of other areas as well, not just network administration. Putting that all together, let's go back to our deploy.yaml. So for each of the routers in the inventory in the route reflectors group, it's going to install this role, and in installing that role, it's going to generate these configurations. And same goes with pushing the config to the devices themselves. It's going to do it for each of those. All right, so that's the gist of it. That's the first role, PE route reflector, but it's very much the same for each of the others. It's just the settings are slightly different. And that's basically the same. So yeah, we have the same three things. Create the output directory, and Ansible is idempotent. So even though I've declared this multiple times in each of these roles, if the directory already exists, it's not going to recreate it. So it's safe for me to put this in here. And then creating the client configuration and then pushing. It's exactly the same processes we just showed in the other role. Now the CE router, let's take a quick peek at that. Same thing, creating the output directory if it doesn't exist already, creating the router configuration, and pushing the configuration. So again, same exact process. The difference being the CE devices are iOS, not iOS XR. So we're using a different module here called iOS config instead of using iOS XR config. But it's a similar mechanism. It'll connect and deploy the configuration if it's different than what's currently on the device. And lastly, because of the way iOS works with interface commands, you know, specifying shutdown or no shutdown in the configuration, if the interface is down and I put no shutdown in the config, it's going to replace that config every time because no shutdown doesn't appear in the configuration when you do a show run. So because of that, Ansible thinks something is different every single time, and thus it will push a fresh configuration every single time. So for that reason, I push the configuration first, but I don't mess with the interface status. And then I have a separate task for turning up the interfaces on iOS. And we use a special module, an Ansible module called iOS interface that's specifically built for handling physical interfaces. So you can say with interface enabled, make sure it is enabled. Make sure it's no shut. And then with items, this is kind of you're doing a for loop here in Ansible language. So it's just the same as any other for loop. In Jinja, you saw the for loop syntax. In Python, this for loop syntax is, you know, is very similar. But anyway, this occurs in the Ansible playbook itself. So I can say for each of these two interfaces on this device, I want to run through this stanza. So we'll configure that interface and make sure that it is enabled. And that's it. Let's see if our network's back up. All right, so everything is good. Everything is reachable. So everything now should have a management interface configured. What it doesn't have is SSH enabled. That's because when Cisco VIRL spins up these routers, it does not generate SSH keys. So even though SSH is enabled, it's not functional. Telnet is, but Telnet is on the management interface. So I wrote a bootstrap script that will help basically take care of getting those SSH keys installed on the devices and activating SSH. So what this does is we have a list of our devices in the topology and credentials for them, and we reach out to the Cisco VIRL API and get the current simulation. So if you look in here, this is the simulation name, end to end, and then a random string of characters. That changes every single time you deploy in VIRL. So we wrote a function here called getSimulation that connects to the API and requests a particular API path. And then we do, we're looking for the topology that begins with end to end. And then we return that as our active simulation. So once we have our active simulation for devices, so for each device in this data structure, we're going to get the console data. So again, VIRL randomly chooses a port on the VIRL host for the telnet connectivity. So we have to find out the telnet IP and the telnet port for each of the active devices in the topology because it changes every time you start it up. Calling the get console data, let's look at that function. Now we're going to pass in the simulation, which is the active simulation that we just found in the prior function. And then we're going to pass in the device host name that we're interested in. We're going to hit this API endpoint, and it's going to return to us an IP and a port number. And then we're going to return that as host and port. All right, so once we have that, for each of the devices, we're going to use pexpect, which is Python expect, and it's a low-level library for telnetting into devices and issuing commands and so forth. Since SSH isn't configured and there's no way to automate the generating of SSH keys using the crypto key generate command, that's what this is doing. So it's connecting, it's figuring out, you know, where the prompt is, it's authenticating, and then once it's to a place where it can issue this command, it issues crypto key generate RSA general keys, and it asks if you want 2048-bit key, yes or no, and you say, you just hit enter, and it'll generate it, and then we exit. So this script will do that, all of that for us. And then there's one more Bootstrap script file. It's using make. Make is a really useful tool to just allow you to automate all the commands that you might run at the command line. So in this case, I've got a sequence called Bootstrap, and it does two things. It copies our SSH key signature to the LXC management container in VIRL, and allows us then going forward to authenticate using public-private key pair. So we don't have to type in a password to get to the LXC management container. And then secondly, Python bootstrap.py, which is the bootstrap file we just looked at. So once it does both of these things, Ansible will actually use the LXC container. It will authenticate with private key. It'll bounce through it as a jump box and be able to connect to the routers in the topology. All right, so now that that is thoroughly explained, hopefully. So if we look at our current environment, let's just take a look at this router here, and we'll telnet to its console port. Just going to validate that there's no configuration on this. This is a fresh deployment. All right, show run. There's some basic configuration here that VIRL has done. It's given us a management IP address on the management interface, but no other interfaces have real configurations. Okay, let's go ahead and disconnect from that. And now we'll run our bootstrap, because as it stands now, I would not be able to SSH into these devices. It won't work. All right, so we'll run the make command and then bootstrap. And that passes in our key file to LXC, and now it's logging into each of the devices in the topology and executing the crypto key generate command. So now that that's done, we should be ready to connect with our Ansible playbook. So we'll run Ansible playbook. We'll point it at our inventory file, and now we'll run our deploy.yaml script. All right, so it's generated the configs for the route reflectors, and now it's pushing the route reflector configs to the route reflectors. And since this is a brand new configuration, it takes a little bit longer, so it's going to be a couple minutes. All right, it's run through and configured both of those, and now the next stage is the route reflector client. So it's generated the configs for all of them, and it's deploying it now. So while it's deploying it, let's take a look actually at the configs that were generated. So we should see here, I have to probably refresh this screen. Oh, there it is. All right, here's the output directory. So far, it's generated our route reflector configurations. That would be this one and this one. And so you can see, remember if we talked about the for loop and the Jinja templating, we've got, instead of just one stanza here, it's generated two stanzas since we had two different VRFs configured in our variables file. And all of the interfaces have been configured with the correct MTUs, correct IP addresses, and OSPF is configured, BFD is configured, BGP, all of our neighbor statements, and then our IPv4 unicast, VRF, BGP config stanzas for each of our VRFs is configured as well, and LDP. So all that's well and good, and let's take another look. Okay, so it just finished configuring our CE routers. I'm sorry, the provider edge route reflector clients, and then it also ran through the CE routers as well, generated the configs and pushed them to the devices. So you can see we have two changes for every device. Well, we have 3 changes for this one. So this was the first one. The first change is creating that output directory. So that did change. And then we have generating the configs. That's another change. And then the third change is pushing the configuration. So in this case, the config was not matching on any of the devices, so every single one got touched. So if we run this again, you'll see the idempotent nature of Ansible, which is what is so nice about using it for network automation. If there is something that is already configured, it's not going to configure it again. In the network world, that could be dangerous if you configure something and then you run a playbook again and you reconfigure it, something like BGP, it's possible that you could flap the BGP peerings or something like that. It depends, I guess it's platform dependent, um, but there's a potential there that things could bounce just because you issued config statements again. We ran through it again, and in this case, nothing changed. Nothing needed to change. Everything was in the state that we requested it to be in. So now that we've done all that, let's take a look at an actual device and see, let's see which one we want to connect to first. Let's do an end-to-end test. So we're going to connect to one of the customer edge routers. And in this topology, each of the 4 corners is configured with a loopback address. This is 1111. There's another with 2222, 3333, and 4444. So that simulates our customer networks. So if we, oops, that's not what I want. If we connect to the one in the bottom left, the CE router. Okay, so now that we're in this router, let's do a show IP route. Okay, so we have several BGP prefixes. Everything's starting to look good. You can see our 4 loopback interfaces at the 4 corners. Our self is 1111. It's directly connected on loopback 1000. And then you can see 2222, 33, 44. And those are at the other sites. So it looks like our MPLS is converged, BGP is converged, everything is good to go. These interfaces here are test loopback interfaces on the provider edge routers themselves. I just did that for testing, but these are the customer prefixes that really matter. And then these are just transit interfaces in the MPLS network and on the customer equipment as well that is in this VRF. All right, so let's ping 3333, and we're going to source it from loopback 1000. You can see it's a success, so let's take another look, and instead of doing a ping, let's do a trace route. And you can see it traces through the network, and it's hitting the MPLS network, because you can see the MPLS labels there in the trace route. So we are good to go. This is functioning as expected. Okay, and that is the end of the demo. So as you can see, it might seem like, I took a significant amount of time to generate this entire playbook and all of these roles and all of the scaffolding around just doing what it is that I'm trying to do. And maybe I should have just used that time to deploy it manually. Like, how much time did I really save? But the benefit here is I can consistently deploy this with no errors. And if I do make an error, I modify the template and I redeploy and I fix my error. Or if I wanted to add an additional feature, let's say I want to change timers on BFD, I make a simple change in the template and I redeploy and it's good to go. And then there's also the fact that this is just a simulation of 4 sites, but in reality there's much more than 4 sites. So in the real world, I'm actually saving a significant amount of time because really all I had to generate was actually 3 configurations. That's it. I had to generate a config for a CE router, generate a config for a route reflector, and then generate a config for the route reflector client. And when I generated a working config, I templatized it and I don't have to do it again. All right, well, that's it for this demo.